doing velocity estimation and some other aspects of things you see with this type of solution. Is this, oh, it's off. That's a good way to do it. Okay. Yeah, that's better. Okay, so the general layout. So GLOBK, what we want to talk about is, what do you use GLOBK for? Its purpose, the common ways that it is used, some of the processing strategies, the naming conventions, which you'll see in GLOBK are very, very flexible compared to GAMIT. We'll look at the important concepts in Kalman filtering. Actually, you didn't cover least squares, did you? Are you going to cover least squares tomorrow?
No.
Okay. Okay, well, just think of least squares. Well, Kalman filtering is a minimization estimation, the same as least squares is, except it has the concept that the things you are trying to estimate are actually changing while you are collecting data to try to estimate them. And that changing of the parameters with function of time is called the process noise. And so Kalman, GLOBK is a Kalman filter where the process noise assumes that there can be essentially white noise changes in positions in every time you make an estimate of it. So a station coordinate every day has a random change that it might have, and that process is called a random walk or Brownian motion. And so we use that very common. It's very good in Kalman filters because it's one of the easiest things. It's got the smallest amount of things you need to estimate to incorporate it in there. So we'll look at that general concept of Kalman filters. We'll look at how GLOBK decides what you want to estimate. And again, it's a little different. In GAMIT, you you say baseline mode, and that tells GAMIT that you do not want to estimate orbits, that you want to estimate station coordinates. And there's also, in the CES table, there's information on how you want to do the atmospheric delay estimates. So you're pretty explicit to tell it that. And then the ambiguities, etc., those all are implicitly there. You don't tell it anything specifically about that. In GLOBK, it's a little different because there's many more things you might want to estimate. And so we sort of use a philosophy. I'll go through how you go about telling it. Unlike many programs where you say, estimate this parameter, and this parameter, GLOBK, you basically tell it what things you don't think you know, and then it will work out what it needs to estimate to let you work out what those things are. So what you're telling it, essentially, is what is your a priori uncertainty in certain things, and then if you're uncertain about them, it will estimate them. If you're not uncertain about them, it will either ignore them or basically it ignores them if you don't think you're uncertain about them. So we'll look at that.
So if you are very deterministic about something, or you are not, you do not have covariance of any quantity, for example, you do not have estimate of covariance initially, then it will assume that it is a deterministic quantity and constant, is it? If
you tell it zero process noise, it'll make it deterministic.
Okay, and it separates out from the number of variables.
And then it's no. Okay. So and it's also, it always starts with you're giving it covariance matrices and solutions from other things, and that's what it's filtering, is those input covariance matrices and solution vectors. And you're telling it what the intrinsic process noise is associated with those things. So anyway, we'll talk about how it does that. Then we'll look at the main modules, which is the GLOBK itself, which is the main processing Kalman filter. GeoRed, I think we mentioned that in the other lecture, it's a small program that actually just sets up multiple runs of GLOBK. But it uses exactly the same command line. So people get a little confused about that. But what it's doing is simply taking that command line, feeding it to GLOBK, and giving it a set. Instead of just processing one thing, it does a whole series of days at the same time. And then there is GeoLog, which is the reference frame realization and post-GLOBK estimation process. GeoLog is built into GLOBK itself, but it also can be run as its own separate program. In fact, GLOBK has that characteristic that its main modules are in fact separate programs that are all blended in the one program. So most of the things you can do in GLOBK, you can actually run a separate program to do if you wish to. And that's sometimes useful for doing things like if you want to save your result and you didn't set it up to be saved in the original place, there's a good chance you can run the program called GLSave that will actually save it afterwards. Or if you want to re-output your result, you can use GLOut to re-output it again. So, so the GLOBK overview, as I said, we're going to review that GLOBK, how the program flows, the GLORG, and the flow of the programs as we go forward. So again, GLOBK is a suite of programs, and it's a bit like GAMIT. GLOBK is what we call it, but there's many other bits that go with it at the same time, and it's designed to combine geodetic results together. And so the phase processing from GAMIT, as you can see, those runs we were doing, we're using 10, 11 stations, and they're taking 10, 15 minutes or something, maybe less than 10 minutes to run. But the runtime on GAMIT is going to go as the cube of the number of stations. That's primarily because it's dominated by inversion of the normal equations, and that's going to increase linearly in size with the number of stations, and the size and matrix inversion takes a cube of the length of the size of the matrix inversion. So when you're dealing with 50 or 60 stations, you're looking at 1 to 2 hours to do it. So the GLOBK processing, that can be done much faster. So when you want to look about you remember in GAMIT we're constraining some stations. And if you wanted to change those constraints in GAMIT, you'd have to run GAMIT again. And that would, if you're doing 50, 60 stations, that would take another 2 hours to do. But if you do it in GLOBK, you want to change the relative constraints between stations, that takes literally a few seconds on a 50 or 60 station network. So it's that speed up by manipulating the covariance matrix and the solution vector rather than going back to the original phase observation. For those of you who have done estimation, it's essentially an estimation, a sequential estimation technique. You're adding a new estimation on top of the covariance matrix that you already have. And so it's also used to combine many days of data together, years of data, and then if you have large networks, I think we were talking about a potential 500 station network in India. Well, 500 stations in GAMIT, you're not going to run that as one network. That would take way too long, and actually you don't have even the CPU resources to do it. It's too big a matrix. So you're going to run 500 stations probably as 10 50 station networks. And that to combine it back into the 500 station network, that's what you use GLOBK for. You have the 10 individual solutions. GLOBK puts it all back together into a single network for you. So it uses as input data what we call quasi-observation files. They're binary. I'll show you how you generate. And they contain geodetic solution information, generally with loosely constrained full covariance information. We get most of these from the GAMIT solutions themselves, but the very common practice now, and we'll talk briefly about it, is from these solution independent exchange files or SINEX files that get generated by different groups. The International GPS Service or GNSS Service, IGS, makes these available on the CDDIS website through their FTP archive. We make them available for the plate boundary observatory processing. So if you want to play around with a full 2,000 station network with full covariance matrices, you can download those files from the PBO site at UNAVCO, etc. GLOBK itself is what we call a smoothing Kalman filter, and it incorporates a random walk process noise in its estimation, and that's a way we can account for temporal correlation in noise. And again, its two main things it's used for is to generate velocity field estimates and time series in a well-defined reference frame, and also it can be used to merge large networks together. And again, because of the speed with which this can be done, we generally iterate the system. We'll come up, and that's what we'll probably try to get done by Thursday, is to be able to actually form our own reference frame based on our own time series and try to refine the quality of the fit to our data, more localized to India than we are currently in the solutions that we have. So again, as I said, the common applications, repeatability analysis, that's usually done with the program called GLRED as the sort of front end. It's individual sessions or to combine regional and global global files together. This is partly for orbit control, and again, that is not so critical anymore. Essentially anything post 1996 or so, the orbits that come from the IGS are going to be better than anything you will be able to generate. And even now, the IGS orbits are done with a few hundred station networks. They're a combination of 8 different analysis centers. They average out a lot of the errors that happen. So it's very difficult for even us at MIT to do a better orbit. We actually contribute our orbits to the IGS. And when we do time series analysis using either our own orbits or using the IGS orbits, it's very, very close in terms of quality, and often the IGS orbit is actually better than our own orbit. And it has a lot to do, particularly if you're doing globally large stuff. On relatively small networks, it makes no difference because the orbits are of such high quality that you can't tell the difference anyway. So you can combine sessions together to get average positions over a survey. So if you do have survey data, spans, say, a couple of weeks where you've gone to different sites, you'll be able to blend them all together to make just a single solution for that survey, which is a useful way to do that type of data. That helps reduce the number of data files that you ultimately use when you do the velocity solutions. The combined average positions you can use to estimate offsets and earthquake offsets and post-seismic motions as well. One of the things when you get a lot of data, the thing you will find the problem is every time an antenna is changed, typically the station position changes. Even if it's the same brand antenna that's put back in place, even though you know you've done force centering on it, which brings it back within sub-millimeter of where it was, you'll find the apparent position changes by a couple of millimeters. And that has to do with the phase center variations on the antennas and on the local multipath environment in some cases as well. One thing to keep in mind, if you run GLOBK in parallel in the same directory, you should be careful with some of the scratch file names that we'll talk about later on. But always keep that in mind if you're running in parallel. So the scenario, why is GLOBK so, people, I'm not sure you heard, but everyone always considers GLOBK the really complicated part of this whole system. And why does that happen? Well, you start with a very simple set of results coming from GAMIT. As you saw, it didn't take us very long to set GAMIT up and run it. And we did things so that data, and you might imagine we've already done it, right? We've done data spanning several years. And we've done a couple of months, we've done a month every 6 months or so throughout the year. And now you just want to estimate velocities from that thing. Well, the complication starts because, well, what reference frame do we actually want those in? The one we used for GAMIT was this ITRF 2008 thing that was in the tables directory that we said to use. What is that? Do you really want to use it? Well, there's ITRF 2014 results out there too. Why didn't we use that? So what do you actually want to do? Do you want to do it in the global reference frame? So in a global no net rotation reference frame, everything moves, and on average, the system has 0 rotation. That's what the name means, if you average it nominally across all of the plate areas. You can imagine that also gets complicated because the boundary areas, things are not moving like rigid plates, etc. But generally, that's not a very meaningful system. Generally, if I'm looking in India, for example, I might want to know, well, how's India moving relative to the Himalayas or to Eurasia? Or if I'm looking further south, how is the Namibia plate moving relative to India? What's the interaction going on in there? So generally, you want to do something else. You want to do something local. If you're looking for subsidence around New Delhi, I'm not sure, I presume every city seems to subside, but if you were looking at that, you want something local around New Delhi, right? You don't want this international global thing. So you have to make that decision. So that's the first complicating thing, is you have to decide how to do that. What if there's been some earthquakes? So we're going, we're not going to span any, are we going to span the Nepal earthquake in the data set we do?
If you want, we can cover the April and Nepal.
Yeah, but anyway, we will have that issue ultimately when you do a lot of data. You're going to span an earthquake. What do you do about, that's your question, right? What do you do about earthquakes? Equipment changes. Again, you're going to span. We actually are already going to see this, right? The station we started to process in 2011, unbeknownst to me, turns out to have the data we're processing in 2013 has exactly the same name, but it's actually a physically different location by several meters. And it's a different receiver as well. So what do we do about that? Some receivers don't work that well. I think you were complaining about the Trimble, right, as having a bit of bad data coming out of it, and it's generating poor quality results. What are we going to do about that? Because maybe the site's going to be off. We're going to find out how it looks when we do it, but maybe we'll have some data off by a few centimeters. What are we going to do about that in that? in terms of this whole reference frame issue, if you're going to do 20 years worth of data, the whole system is going to evolve during that period of time. How do you handle that type of situations? Which ones should you use? Which ones are the good ones? You know, we just looked randomly around the IGS network to choose stations to process. And in fact, if we're starting a process like this, that's often what you do. You do a preliminary analysis over several years, but just a few days here and there. And then based on that, you decide, okay, this is what I really want to do. I don't want to include that one. I want to get rid of that station. We were thinking about Dagar. I thought it didn't look good, but actually when we looked at the residuals, it was okay. So there's lots of other things you might want to change and how you end up doing that. And so you want to decide to add global sites. So we chose some IGS sites, but you don't want to go back to all that time-consuming GAMIT runs. What are you going to do about that? And that's a thing we'll discuss. So the GLOBK command files are actually designed to handle all these cases, but each one of these things is very unique to each person's analysis that they're doing. So there's no single solution here. We're going to give you a template, and we're going to start with some templates, and then we're going to evolve those templates. And as time goes on, I must admit, they can get quite complicated in what they contain, but it's all typically incremental each time as you fix a problem, take something into account as you go across. So GLOBK, the processing stages that we have. The first program you run is called H2Global. And that generates the binary input files that you're going to need for running GLOBK. Again, if you understand how Unix wildcards work in directories and stuff, this is generally a really simple thing to do. You can have all of your data converted all in sort of essentially one step as you go across. So GLOBK itself, when it runs, has several unique steps that it goes through. There is an initialization step, and in that step, all the headers of these binary H files are read to determine the nature of the solution that is actually being given to it. So that's the parameters that are being included in this, what's called the state vector in the Kalman filter. It's just simply the things you are estimating. It works out all the different site names that are there, accounting for all the different offsets and earthquakes. So there's a set of information in the GLOBK command files you have to give it first so that it can do this calculation correctly. It's only a few things. If you get it out of order, it actually tells you instantly that you've got it out of order, and it's easy to fix. So it's not a big issue, but there are certain types of information you have to give it first before you start. So once it's done all of that, it actually initializes it, and it comes up. You give it a list of files. Those files that you've given it, could be generated anyway. It actually does time sort them automatically for you, and so you don't have to worry about that. And then it does a forward Kalman filter run. And so a forward Kalman filter run has potentially process noise in there. But if you're interested only in what we can call the deterministic parameters, the things potentially like your final station position, your final velocity estimates, at the end of the forward run, you have all the parameter estimates you have. And so that's where you would stop. If you are interested in getting sort of more information about this variation with time, you can run a backwards running filter. It's the smoothing Kalman filter. When you do that, actually it's not that common. There's not very much need normally to do this except in special circumstances. You just have to keep in mind that when you run this, it actually takes about 1.5 times longer to run it, because you have to run the filter backwards in time, which takes the same length of time as the forward. But there's actually a big step of actually the smoothing loop, which takes about half the time it takes to actually implement the Kalman filter. So this, most of it, as I said, you don't normally run this backwards filter. There's a simple output, which is a program called GLOut, but again, you don't normally explicitly run it. And it just literally is an output of the solution which you just generated. It generates a thing called what we typically name as a .prt file for print. Sometimes we actually don't bother outputting this at all, just because we'll find out that the way we run most of the solutions, what comes out of that is still quite a loose solution. The big step is this, what we call the reference frame realization. And that's done in this module called glog. And it also allows us to do post-solution constraints. So what happens here is when we run GLOBK, our standard approach is to keep all of the station coordinates loosely constrained. So when GLOBK finishes, it's stacked everybody together, but the absolute coordinates are not well known. But again, if you extract things like baseline length, you'll find those are very well determined, just the absolute coordinates. So this GLOG model, and it stands for global origin essentially, is a thing that's going to transform that into some particular reference frame. And it's going to do it by rotation, translation, and possibly scale, and not all of those necessarily. You can just simply translate it if you wish, or sometimes you just want to rotate it, depending on what you're doing precisely. So you have options of which ones you want to do, and it's going to work out the best estimate of how to rotate it to align it onto a certain set of stations and their coordinates and velocities. And it then also propagates that through the covariance matrix to actually get you the covariance matrix in that realized reference frame. So the print file, typically the uncertainties of the station coordinates are several meters. In the GLOG file, after reference frame realization, they're generally down at millimeters and better. And that's done through this rotation, etc. So, and then you can also in here, when you have large complicated solutions, you often have breaks in the positions because of antenna changes, but the velocities are expected to be the same. So you can tell it to equate velocities. You can tell it to equate different, if you have sites in a nearby region and you want them all to have the same velocity, you can tell it to equate that information as you go across. You can also estimate things like plate poles. There's many things you can do this post-estimating with GLOG. And then finally, you may want to actually save your solution in a file which then can be used later in another GLOBK run. And you do that with a command called out global, or it can be done with the program called glsave. And so this is what you do when you're, say, combining the 10 networks together to form the 500 station network. That solution you would actually save as a binary file, which then later on you just treat all the 500 station files. Or if you are doing campaign data, you might have 2 weeks worth of data. You combine it all together and save the results. So you have one file that contains all of the survey results in that one single file. So as I said, the modules in GLOBK can be called within GLOBK itself as subroutines, or they can be run externally as standalone programs. And all the program names, even though I'm putting here uppercase on some of these, all the program names are actually lowercase. And you do have to have the case correct. So you can also bring in non-GAMIT files into GAMIT. This converts many different file types out there. There's a caveat in that many of these file types do not have the same level of bookkeeping that we have in GAMIT. So it turns out that we copy through into our files information about the ocean loading you used, what sort of atmosphere models you used, etc., the tide model you used, and that is kept intact in the files. These other file formats often don't have that information, and so we can't carry it through. So, so you be a bit careful about the metadata that's actually in there. There's also sometimes SINEX files come in what they call frame-resolved versions. So these are not loosely constrained solutions anymore. They are actually have the millimeter level uncertainty coordinates in it. This is very common if you get them from PPP solutions. And so for things like the gauge and PBO frame-resolved files, and actually even the IGS frame-resolved ones, there's an option that allows you to translate and rotate to put back into the covariance matrix the uncertainty due to translation and rotation. And you do that with an option in H2Global. H2Global does do dynamic memory allocation, but it doesn't know before it starts how much memory it's ultimately going to need. And so it has a default value it uses, but sometimes it'll run out of memory, and it'll tell you fairly rapidly. So there's a -m option that allows you to set the amount of memory you want to allocate. So for things like the PBO files, which are 2,000 or 3,000 stations, you need to allocate about need about half a gigabyte of memory to actually read those files in successfully as you go across. The IGS SINEX files, you can also use this -s option, which does a name translation to make them consistent with the solution as we come across. Whenever you read these other files in, the covariance matrix uncertainties are very, very different from what you might think. In particular, if you get solutions from the Bernese package, it turns out if they are normal equations solutions, you need to actually multiply the covariance matrix by 10 to the minus 4. It is so over-scaled. It seems to have massive uncertainties in it. And I think it has to do with the way that they do their normal equation scaling. They don't scale the normal equations by the unit variance. And then other things they do makes it all too small. So, and everybody has a different way of treating errors. So you have to normalize out the errors between these other systems if you do that. So there's H to global, the functions in the flow. So H to global translates, so you typically start with that, and you would start with a GAMIT H file, which might be called, something like HEMED 10, it's year and day of year. That, by default, gets translated into a binary globe file, which has the year, month, day, hour, and minute, and then the name of the 4-character session code name that you used gets put in. So ours are all going to have GIAN on them at this point. And then this becomes a list of files, and you basically just do an LS on the GLX files. The X stands for the biased fixed solution, and you put that into a file, which we typically end in GDL, the global directory list. And so typically we use 3-character extents, which is fairly consistent with the way things used to be done. And so you generate this file just simply with an LS. The GLOBK command file you want to use, we're actually going to look at one which is, we could start with the COM one, but we'll probably also look at one which is called GLOBK long. It's again a template. That template is set up to use the ITRF 08 system of a priori coordinates. You run GLOBK, that generates the output print file and a log file, and then a binary solution file, which is just an internal format. And then the COM can be used in glorg, and with that we list the number of sites that we want to use to define the reference frame. And we call that sort of the stabilization list as we go across. And the glorg module outputs the org file, and then you can also run things in glorg if you wish to as well. So these names all can get chosen arbitrarily, and again we tend to keep the extents the same. And this is sort of the standard default template at the moment for doing things. So the GLOBK command files, GLOBK itself is controlled by a command file that instructs the program what to do. So the command file contains a series of classes of commands in them. There's what we class as the estimation commands, and they tell GLOBK what you want to estimate. And they are put in sort of essentially 2 different ways. They have a generic form of APR underscore, and then a group of letters that describes what it is, and MAR underscore, a series of letters. And those tell it the a priori uncertainty on what this quantity is, and MAR tells it what the process noise is if it's a stochastic parameter. And those process noise, the units are in typically whatever the units of the parameter is squared per year. That's the standard random walk number as you go across. And we'll talk about what the XXX in a minute is, which ones you can use. There's also a priori information about coordinates, and then information about discontinuities in times and site selections. And then there's commands which sort of control the output of what you want to do, and then control commands that tell it things like that you actually want to run glorg at the same time. So this is in the GLOBK command file. There is the glorg post-processing program, and it also has its own command file to control how you want to do that frame realization and other things you might want to do on the post-processed solution. So the simplest GLOBK command file you can have would have one line in it. Just says APR, northeast up, all, means all stations, 10 meters, 10 meters, 10 meters, and 0 on velocity uncertainty. So 0 in the a priori velocity uncertainty means that you do not want to estimate velocity. And so this will then basically take your data, and it will just blend everybody together and give you a solution. It'll have large coordinate uncertainties because of the fact that nobody's particularly constrained here. But again, if you look at the separation between the sites and the baseline lengths, you'd find those are well determined. And there's an output option you could add to this to get that output if you wish to. So in general, you have several more commands than this, and we'll look at those examples in these GLOBK XXX templates that we actually supply with the solution. So the file naming conventions for GLOBK, they're arbitrary. However, we do follow a certain level of convention. The binary H files from H to global, we typically end them as .glx. These automatically get ended in .glx for the biased fixed solutions. There's a GLR version, which is the biased free solution. So you haven't tried to resolve the ambiguities in this solution. You only use this if you think there was something wrong in the ambiguity resolution in GAMIT. So again, generally, we do not use those ones. The list of binary files you want to process end in .gdl. The GLOBK and glorg command files, we typically start them with globk underscore, and then a type that is of your own naming to represent what you want to do with this particular one. And glorg, we typically, if these are linked together, we keep the type the same. The output files, the print file itself, we typically end in .prt, and often we don't output that file anymore. And then the glorg output is .org, and then the log file, which you can look at to see what's going on while you're running, ends in .log. The a priori coordinate files, we typically end in .apr. We have a set of files, set of files, which allow us to specify when earthquakes happen and any renames that we need because we have misidentified a station or because we've changed an antenna and we want it to be treated as a separate site. And those we typically call a .eq file. And then the list of stabilization sites we want to use, we often end that with a .stab for stabilization. Again, you don't have to. That's what we tend to do. So we'll come back and look at how those things interact with each other as we go across. So Kalman filtering itself, it's the equivalent to sequential least squares, but the estimation allows for stochastic processes. And again, we're using a random walk, which is a class of first-order Gauss-Markov process. So this random walk is allowed for coordinates, Earth orientation parameters, network translation scales, satellite parameters. And in this random walk model, the uncertainty in your parameter, the idea basically is you are estimating a parameter, and at some point you know what it is. But as you wait in time, your uncertainty gets bigger on that value. So in a random walk, the value remains constant, but its uncertainty grows, and it grows such that the variance increases linearly with time, or the standard deviation goes as the square root of time. Any of you who have done precise leveling, so anyone done precise leveling or learned about precise leveling? Okay, only one, okay. Anyway, there the standard model is square root of distance, right? Yes. And that is a random walk. That's the same model in precise leveling. Except there it's not time, it's in how far you go. Every measurement you make has a random noise, and that will grow. The standard deviation grows as the square root of the distance you've traveled because you take constant length steps, 50 meters or 25 meters, whatever. Same process. So that's how you can calculate quickly for the number you get, how much is it going to be 1 year later? How much will this add on my uncertainty? So the Kalman filter works because so Kalman filters work in covariance matrix space. So those of you who have done least squares, weighted least squares, it works in what we call normal equation space. So the normal equation and the covariance matrix are just the inverse of each other. And that fact that Kalman filters work in covariance matrix space means that it cannot have, if you have a normal equations with 0 in the thing, you can't invert the matrix, right? Because it implies infinite variance. So you can't have infinite variance in a Kalman filter. So everything has to have some a priori constraint applied. The equivalent in doing least squares is if you were to put something down the diagonal of the normal equations before you started, and an a priori constraint in the normal equations before you start. And so you always have to have those loose parameters in there. If you're really interested in seeing how this all works, there's 2 papers. My paper published back in 1990 in JGR, and then Dong et al. Papers published in 1998. This is a basic Kalman filtering paper as applied to geodetic data. In this case, it's VLBI, but the concepts are basically exactly the same as for GPS. And then the Dong et al. Paper is, Dong was a student of mine, and it's the paper where we talk about combining quasi-observations together. It is the sort of paper that essentially outlines the way GLOBK actually works, although GLOBK itself actually predates the paper by about a decade. And so this gives you more detail on how, and the issues, and in particular Herring et al. In the appendices gives you some insights into the way this process noise works and your sensitivities to it. Dong et al. In its appendices also gives you some insights into the way these transformation parameters work that we're talking about for doing the GLOG type processes. So one of the things people get structurally confused about with this is that GLOBK and GLRED are the same program, but with slightly different ways of treating the H files. So their run strings look identical. And in GLOBK, when you give it a list of H files to process, all of those H files are combined into a single solution. When you run GLRED, nominally each of the H files is processed separately and generates its own solution, although there is a syntactical technique you can use where you can add a plus sign at the end of the name, you space and then a plus sign, and that allows you to add in small blocks slides together. We take advantage of that when we're doing network combination processing, etc. There are certain shell scripts that will actually generate this for you as you go across. And GLRED itself is just a small program that reads the H file and then generates the run string for GLOBK and then calls GLOBK internally. So in Unix, you can run programs from inside other programs with a command called system. And that's basically all GLRED does, is it just sets up the running called system. And as I said earlier the other day, that these days we might actually have made GLRED a script rather than a program as it is today. So don't get them confused. They're both GLOBK. Fundamentally, you're doing exactly the same thing. It's just the way the H file gets treated as either separate units or as one big unit to be processed. So there are two types of files for solution files. There's a H file you can save and that is valid for external exchange and is backwards incompatible. This is basically a binary H file that is written by GLOBK. We maintain backwards compatibility of those files. And then GLOBK itself internally, just because of the size, uses its own scratch files inside. And we have these as the COM file and what's called the SOL file, solution file. The COM file in particular, we do not guarantee that it will remain constant. So if you want to run GLOG by itself, you need to have that COM file, and you need to have the SOL file that goes with it. And so you can do that, but if you upgrade GLOBK into a new version, there is a chance that the COM file you generated with the last version will not work anymore. So we typically also save the GLSave program from each version so that you can use the old version of GLSave to actually write your COM file out as a standard full binary H file and then use it in your new solution. So we try not to make this too hazardous. We also tend to announce when we've made this change. There's actually a versioning number on it, and it will tell you if the versions don't match. And we try to announce that we have changed the version and warn people before they put up this new version of GLOBK, you either save your old version so you can work with that file still, or save that solution out with GLSave into the standard binary final version of that. GLOG is called by GLOBK GLRED, or it can be run separately, as I said. And to run GLOG by itself, you have to use the command called COM file. By default, that command is actually not given, because if you're just running a single network at a time, it's actually, the COM file is quite large, and there's actually no reason for it to actually be written out. And so it just saves time by not doing it. But if you want to run GLOG, you need to make sure. And you need to have this be a unique name if you're doing multiple different things and you want to keep the solutions separate. So the GLOBK command files, the things you have to supply. You have to supply the command files. And so as I said, we have templates that we'll start with to do modification of, but you have to develop that. It's a bit like having to do the sites.default file yourself. You have to supply the GDL file with the list of H files to be processed. The binary H files themselves need to be created either from Sinex or from the GAMIT H files. So that's sort of the minimum of what you need to do. The a priori coordinate files are optional, but we actually recommend that you use them, particularly if you're doing reference frame realization. If you do not give them, the GLOBK will use what it infers from the input H files, which often is okay, but sometimes can be a little uncertain as to what it is. There's Earth orientation files. Again, optional, but if you're estimating Earth orientation parameters, we recommend that you have them there. Again, not particularly critical. And then the EQ files, these are the earthquake files, which, again, when you have an earthquake in a region, the way GLOBK works is you tell it where the earthquake was located, what its radius of influence was, and the statistical properties of how big an earthquake was in terms of the covariance of how big an uncertainty did it induce. And the uncertainty has two components, a static component, which is applied to all stations, and then a component that depends on how far away you are from the earthquake. So when you're close to the earthquake, it's big. When you're far away, it goes to a small number. That earthquake file, and so then GLOBK calculates which stations are actually affected by the earthquake. You don't actually explicitly say that. It also has in it rename commands, which is what we're going to use to compensate for a changing station, and when you change antennas, you have those. So those are all put in the same file. The earthquake file and the APR files, you can actually supply multiple commands. Do that multiple times, and GLOBK will read each of those. And basically, in standard sort of GLOBK way, when you reissue something, when you do a command twice or you do something twice, whatever the latter version is the version that's adopted. And so as we go across. So again, this is optional. We will ultimately need to use this. There's always one of these already for the ITRF 2008 system because of all the antenna changes that affect that in ITRF 2014. Files that are internally generated by GLOBK. There's a little binary file called .crt, SRT, which you don't normally worry about, but it is the actual sorted, time-sorted list of your files. There's the .com files and the .sol files. These .svs files are when you're actually estimating satellite orbits, and all except the .sol file must be named explicitly at the top of the GLOBK command file if you're going to use them. And again, if you're doing anything in parallel, we recommend that these names be unique to the run. There's a wildcard you can use to do that. I'll show you how to do that later. So these are the generated internally by GLOBK. And then the output files, there's output that comes to your screen. There's a log file, which sort of gives you a summary as it's stepping through the solution, so what's happening. There's also those standard gamut of GLOBK status and warning files that automatically get created as you go across. And there's the print file and the org file and potentially the output binary H file from your solution. So then file handling name, the log files and prints by default are actually concatenated together. So when you run GLOBK, if you keep the print file name or this org file name the same, the next solution gets written at the end of that one. That sometimes is a confusion when people change something and then they go and look at the solution and they realize it doesn't look like it's different. But if they look down, they'll actually see there's a second solution below it. That's very important when you run GeoRed, because what you want to do is generate a time series. So each of those individual runs, you want them typically to concatenate into the one file. And so that's why it's actually done that way. However, there is an erase option, ERS, that you can use with the output control files, which is the print opt or the org opt. This is the options for outputting the print file and the options for outputting the org file. And so erase put on this will actually erase any existing files. So again, when you run GeoRed, just be careful you don't have the erase turned on. Should be done. So the com sort files are overwritten every time you run GLOBK. The common sol file should not be renamed because the original sol file name is actually embedded inside of that com file as you go across. There is automatic naming schemes using the wildcards that are available for all of these files. In fact, I think every file you can use wildcards in. And the standard wildcard we use is the ampersand symbol. And what that replaces is you just say com file space ampersand .com. And then the ampersand gets replaced with whatever the name of your GDL file is, with the GDL removed from the end of it. So what we call the extent, with the extent removed off that name, it uses that character string. And that's a really useful way to be able to run these things, where if you keep the GDL files separate, which you normally would, then you can run multiple solutions simultaneously, and they will be saved in their own unique names as they go across. So the estimation rules in GLOBK, which again sometimes can get confusing with one particular aspect. So for a parameter to be estimated in GLOBK, it must appear in one of these APR commands, where x-axis is a parameter type. The most ones you use will be NE up for northeast up. SVS is when you're doing satellite orbits. And then wobble is for doing polar motion. UT1 is for doing universal time. So these are the Earth orientation parameters. And then ATM is for atmosphere. Now the atmosphere is passed through from GAMIT. This only works with the GAMIT H files. It's passed through as a single mean value for a station. It's not the time variation that you estimated in GAMIT. It's actually the mean. And when you look at the output atmosphere estimates in GAMIT, you'll see there's a mean, and then the differences are from the mean as a function of time. The idea of this command is when you do network merging together, the common sites between the networks, this APR atmosphere command will make the atmospheric delays the same at all of the common sites. It turned out not to be as impactful as we thought it would be, and you can play around with turning it on and off to see, but it does, but that's what it's doing, is it's trying to make the atmospheres the same, atmospheric delay estimates be the same at the common sites when you do networks together. If a parameter is not mentioned, it does not appear in the solution, and if it's actually in the input H files, the treatment effectively is that its covariance remains unchanged. It implicitly does whatever it needs to do to actually be consistent with what's going on, but you just don't know what the value of what it did. So it's, this becomes important if you were to say do a relaxed solution in GAMIT, where you're estimating satellite orbits, and say you did 5 networks. If you did not use the APR SVS command to explicitly estimate orbits, each one of those networks would literally have their own separate orbit determination. And it's by putting in that explicit estimation of the orbits which tells GLOBK to link those parameters together. So again, this is more of an issue when you do things like orbits. It also happens with the atmospheric delay. If you did networks and you each one of the stations would have their own separate atmospheric delay estimate, and you wouldn't be able to see what it was, and it would be different for each one of the networks. And again, actually, it doesn't do that much harm to do that. It weakens your solution as you go through. So if it's not estimated, it doesn't go, and it stays whatever the implicit uncertainty it has. So as I said, if the orbits are estimated in GAMIT, and you want them constrained in GLOBK, use that. If you do not, the orbits are left unconstrained. And so they wouldn't be linked if you had networks, and often, once you've actually generated a merged network for an orbit, you don't care about that orbit anymore. And so you do actually take it away on purpose at that point, so you don't have to carry all these extra parameters which are going to increase the runtime as you go across. If 0 is given, this is the most subtle point in here. If you give 0 as an a priori sigma, then the parameter is not estimated. It is not fixed to a 0 uncertainty. So it's a little inconsistent in the way we've done this in a sense. But 0, basically, since that's the initial state of everything, 0 is used to indicate that you do not want to estimate it explicitly. So if you actually want to force a parameter to its a priori value, then you can either give it a really tiny a priori sigma, a just non-zero value, or we actually explicitly allow you to give f for fixed. And interestingly enough, in Kalman filters, because they work in covariance matrix space, you can give 0 uncertainty to a parameter. You cannot give 0 uncertainty to a parameter in a normal equations and all these square solution. Because no. In a standard least square solution, if you have a parameter and you say, I want to give it 0 variance, to put that in the normal equations, you have to invert that matrix. Weight matrix, and then the weight matrix goes infinite, and it doesn't work. In Kalman filters, you can do that easily. That's because of the difference in that. So in Kalman filters, you can't start with 0 variance for something, which, so you can't start with infinite variance, which implies a 0 normal equations. You have to start with something finite. But you can start with 0 variance, which would imply infinite normal equations. And so you can't do that in least squares. It's because they're inverses of each other. And that's why this f actually doesn't translate into a tiny little a priori sigma. It translates into 0, and it is actually a forced to fix to that value. And
Does it add some random noise?
no, it's 0, literally 0.
Literally, so the moment you make the weights in the Kalman
We don't make the weights.
weights, okay.
So that's the whole thing. Kalman filters work in covariance matrix space. There is no weight matrix.
So we not make any inverse of the covariance matrix?
Nope.
Okay.
Nope, you never invert. The only, you have to, you can also have 0 variance data,
Yeah.
but you can't do that in least squares either.
Yeah.
But I mean, again, because you never invert the data covariance matrix itself. You always have the data covariance matrix with the uncertainty in that data space implied by your current uncertainty and your parameters. And so you can have 0 variance on the data and still successfully run. So it's, again, if you just think about it, they're inverse space of each other. What's possible in one is not possible in the other because of that inverse nature. So anyway, if you want to force a parameter, you give it f. Again, we normally don't do this. Well, the one case we do this is for something like the satellite axis antenna position offsets that we estimate in the GAMIT IGS big global H files I'll talk about. We have those estimated, and when you run with your regional network, you don't want those estimated, so you will force them with an f to be 0 variance as you go across. So the parameters, the other important thing to remember is that the parameters in GLOG must be kept loose in GLOBK when you're doing the reference frame realization by rotation and translation. So the idea is the algorithm in GLOG assumes your system is rank deficient. And for rotation, it is rank deficient by definition because of the way that we allow the Earth's, because the Earth's rotation varies so much. Translation in GPS is sort of rank deficient. Although when you have, if you have the orbits free, it's very poorly determined, so it's close to rank deficient. When the orbits are fixed, the origin is pretty well set. So we'll talk about that when you do translation for your reference frame, you should be explicit about estimating that translation. Scale in GPS, we heard the other day when we talked about coordinate systems that people often do a seven parameter helmet transformation with scale. Scale in GPS is not rank deficient if all of the satellite antenna offsets are fixed. And even actually when they're free, it's still not rank deficient, it's just poorly determined. So scale is one of those cases, again, that in the way the GLOG algorithms work, you have to explicitly estimate it if you are going to use it in part of your frame realization. And again, we could spend a lot of time talking about scale. You'll see, when you look at the IGS literature and what people do, and a lot of papers, people just sort of come in with this natural thing from, I think, conventional geodesy of estimating scale all the time. But what scale is in GPS is the average height of your system. Because the Earth's pretty circular. And if you take a spherical body, scale it, all it does is just push everybody out in height. And so when you estimate scale, what you tend to be absorbing is any average height difference between it. And we know that there's these large scale loading phenomena that occur in the Earth. And when you take regional networks, well, it's a pro or con, and you just got to be aware of what you want to do. When you take a regional network, if you're estimating scale, what you're doing is you're taking out that average height change. And maybe that's what you want to do. But if you don't realize that's what you're doing, it can be a mistake. And so scale is always one of those things you have to carefully think about. So the Earth orientation parameters, normally we use these in two forms. When you do your baseline solutions, we recommend, you should turn these on because you want your system to be able to rotate and translate to align as we wish. And those are done with the a priori WOB for polar motion and UT1. Units are milliarc seconds and milliarc seconds per year. Most of the time, for positioning, you don't need to have the velocity term turned on because you're just going to do it at each one. And 10 milliarc seconds is a pretty reasonable number for the A. We actually know the orientation much better than that number. This is sort of, again, one of these loose constraints. For regional networks, some people like to actually constrain it down. 0.2 milliarc seconds is still relatively conservative to how well we know the orientation of the Earth. But when you do this in the GLOG frame realization, you should not allow it to rotate. because you've now constrained the rotation already. And so you should just allow it to translate. And again, these days, even for regional stuff, we tend to leave the wobble free because it's just easier to let it rotate. And again, it's a subtle issue of the Earth orientation parameters we have are the whole Earth orientation parameters. And when we have these common mode errors across regions that we want to remove, that common mode error can be represented as a rotation and translation. And so we allow a rotation, which is bigger than the rotation for the whole Earth. So again, our recommendation is to stick to this sort of wobble number and do the rotation in geolog. Yeah, so again, sometimes you do need to be a little careful. As I said, the global form is what we normally recommend to use. If your local network is not well surrounded by stations, that sometimes can be an issue. But again, you try when you do your initial network, as we did for the processing here, we try to bring IGS stations from a whole the way around. It's the standard, work from the whole to the part, right? I think is one of those standard geodetic concepts that we have. How are we doing for time? Whoa. Okay. Data editing. So again, when you do things, you end up having sites that are either poorly behaved or do things wrong. So one of the things, and we'll talk about some of the shell scripts that do this, is allows you to calculate the process noise. So if you have a station that is moving around, and later on in the class, in a few lectures from now, we'll show you some really bad stations that move around. And so you can do that with the Markov process noise. And so a typical value that we would use is be 2.5 by 10 to the minus 8 meters per squared. That's about 0.5 millimeter in a year. That's actually that's a really good station. And then worst stations are something like 4 to a bit higher. That's about 2 millimeters in a year of motion. And that's sort of to represent the random sort of motion of stations as you go across. And you do this with the MAR northeast up command. And again, this is sort of the way GLOBK works. This first line, MAR all, says it applies these values to all the stations. And then you give it the list of ones that you want to be different. So in this case, it's a site in China called Chengdu, where we make it a larger number because it's quite a noisy station. This shell script called shgenstats generates these values for you automatically, provided you have a reasonable length of data. And it's really good for continuous data. And if you have 1 or 2 years worth of data and you want to characterize it, this shgenstats is a very useful way to do it. It also ultimately gives you the median value for your network. So if you have stations that don't have enough data, you can always choose the median value to use for those stations as you go across. So this is a very good way to do it. Sometimes you just have individual values you want to downweight. And so if you have a site that on some day just looks noisy because it had bad atmosphere, you can actually do this sig northeast up command. And again, you can do it by individual station, by overall. And this would just add 1 millimeter of standard deviation to the covariance matrix in millimeter in northeast and 3 millimeters in height. All these units are meters. And then you can do it by individual station. And you can also specify a time range over which that happens. So if you have a noisy station and you just want to keep it in your solution, but you want to not make sure it doesn't influence anything, you can give it a sigma northeast up to increase its uncertainty on a given day. It doesn't change its value, it just increases its uncertainty. Sig northeast. Actually, I'm not quite sure what that line actually means. I might have to check the help on that command. Oh, no, yeah. I'll go back and check. That looks like it's applying it for a whole network as we go across. Yeah, let me check the syntax on what that actually means. So that's one way, is to downweight them by applying a variance to them. So if you want to downweight a site completely, then what you can do is just give it a really large uncertainty. And again, in terms of influence, it's always the ratio of this uncertainty to how well normally things are determined. A more preferable way, if you just want to get rid of the site completely, is to put it into the EQ file as a rename. And we have this special syntax that rename a site to XCL at the end. And one thing I should have said earlier is that in GLOBK, the site names are 8 characters long, not 4. And the standard name we have is the 4-character code and then underscore GPS. And it turns out if you were actually processing SLR data, it would actually have SLR in that name, is the standard convention we use. But for GPS, we put that in. And then there's GPS at the end. We actually modify that to account for different things. So if you change the antenna, we'll often call that 2PS, 3PS. If there's an earthquake, the PS part gets changed to a 2-character code. And so we have a special code of XCL, which means exclude. And there's also an XPS, which also excludes it, but in a slightly different fashion. So this is a way to actually take the site completely out of the solution. You don't see it anymore. It's completely eliminated from the covariance matrices as we go across. So if it's really bad, this is what we recommend. If you still want to see the value somewhere in your time series with big error bars on it, then that's a technique that you can use. Okay, so GLOG invokes GLOBK with generalized, what we call generalized constraints. After all the H files are stacked, can be run as a separate program. It allows you to link parameters together, and it also allows estimation of Euler poles for plates. So we could, in fact, if we have plates on India, we could estimate an Euler pole for the Indian plate with the data that we have. We might give that a try, see what happens. So the parameters in GLOG must be kept loose. The station coordinates, the EOPs, and the scale if you are using the scale in the reference frame definition. And it can be used to, and as I said, used to define and refine the reference frame as you go across. So to invoke GLOG to run in GLOBK, the standard way is to actually put in a command in GLOBK, which is just org_command, the GLOG command file, and you give it the name of that. And by doing that command, that tells GLOBK to run GLOG internally. If you do not give it this command, GLOG will not get run. Then there's an org ops, which is the output options that you have. And then there's an org out, which is a file name. Normally, we do not give this command because what will happen is the output org file name will be based on your print file name, and the .prt name, the PRT will be removed, and .org will be put in its place. And so it will, so as I said here, that's what we recommend, because then you ensure that the org file and the print file go together and that you don't accidentally overwrite an org file. If this is a hardwired name in here, every time you run it, it'll overwrite that file or append to that file, depending on what options you have out there. Okay, so in the APR file, coordinate file, which you can also specify in GLOG, does not need to be the same as you used in GLOBK. And this is a very powerful feature because often when we run GLOBK, we will run it, say, with just the standard ITRF, no net rotation coordinate system. But then when we want to run GLOG, we want to do our frame realization, say, in the Eurasian reference frame. So we will give it an APR coordinate file in which the velocities are in the Eurasian reference frame. And that way we can do our reference frame stabilization or realization in Eurasia, not in the other frame as we go across. Or we might give it an APR file with just local stations where we give everybody 0 velocity. And then we'll take the best of those, and that will give us a frame in which we localize out so that on average across the outside of your region, everything is 0 velocity. And that's, again, you can do that. But to do that, you have to have had the coordinates be loose when you ran GLOBK itself, so that you can arbitrarily change them inside of that. So again, the APR sigmas must be large to be able to do that. So to do the frame realization, we have 2 basic commands, posorg and rateorg, and these control what parameters get estimated. So there is xtran, ytran, ztran. I must admit, normally you always do these in triplets. This allows for translation. When you do this, you should turn on the APR tran command in GLOBK in the baseline, if you ran GAMIT in the baseline mode, which is what we normally do. XROT, YROT, ZROT allows rotation, and again, you should have on the APR WOB and APR UT1 commands when you use that. And then scale allows for rescaling of the system, and again, you should have APR scale turned on when you do that. So these tell GLOBK how you want to reorient your frame. So if you'd constrained the orientation, you might just do the translation term. Or if you would If you'd done scale, you may do scale. If you didn't do scale, you should not do that. Now, in doing that rotation onto the reference frame, there is an issue about what weight you want to give to the heights. Now, as I said, heights have a bad habit of being influenced by loading. So you might have a station that's moving nice and linearly, horizontally, or as a function of time, but its height's going up and down with a strong annual signal. And so if you don't take into account that height variation and you try to reorient your reference frame, there will be some bias in the reference frame associated with doing that. And so we have this cond height variance term, which allows you to set the relative heights of the variance. The default is actually actually I forgot what the default is now. Normally it's 10 because the heights are typically a factor of 3 larger in standard deviation. But if you want to reduce the impact of heights, then you can set it to about 1,000 or so. And so this is one of those parameters you can change to see what it does to your particular solution. There's also a stab iter command, which is the number of iterations that you want to do for the stabilization, and also some sigma cutoff information if you want to remove a site. So again, you give this list of sites that you want to use, but on one day, one of those might not be very good, and so you don't want to use it. And that's what this iteration does. It allows you to iterate and take out sites in each one of those iterations. There's also a stab site, which is a list of sites to be used for the frame realization or stabilization, as we call it here. And so those are the main ones you use to control the stabilization of the system. When we do the tutorial, you'll see those in use. Controlling your output here, there is the CRT opt, print opt, and org opt specify the output screens. The GLOBK and glog help tells you what those options are. Glog is particularly good for this. The main ones we use are erase, that will erase the file before writing. No PR means do not actually write the output. Again, we typically use that for the print output, or the CRT opt is the output comes to your screen. So again, when you're doing a lot of stuff, if you're looking mainly at the glog output, you just don't want a lot of clutter on your screen. So we very rarely have CRT opt and print opt set to no print to stop them happening. BLAN will print the baseline lengths. BRAT will produce the baseline rates, and that's also the angles between them. RNRP generates reports on the differences in the parameters when you rename. So when you have a site, you change it, you say it could be a different position because I changed the antenna. This RNRP will give you the actual estimate of the change and the uncertainty of that estimate based on the full covariance matrix as you go across. Fix-A is a way to fix any problems in most of your problems in the APR coordinate systems if you are doing equating of velocities, etc. And again, we recommend that if you equate parameters in glog, that the a priori coordinates be consistent between those two. VSUM outputs a lat long summary of velocities, and you need that if you're going to go on to plot velocities with things like shplotvel, for example. PSUM outputs a lat long summary of your position changes as well. GDLF outputs a list of the H files you actually used, and also the chi-squared increments from that run as you go across. So as this Kalman filter increments each step, it calculates, before it actually does the calculation, it calculates what will be the increment in chi-squared when I put this file in. One of the parameters you can set is a limit on how big that number can be. And again, if you're doing a very large solution and you want to make sure it gets through, and you might potentially have a bad H file in there which has some station that's just really weird or something, then you might want to stop it incrementing anything more than 10, or maybe even 3 or something like that. And so depending on what you're doing, it will tell you what that increment was, and you can limit it so it doesn't get added in. Or if you put this output, it'll have a used or a not used at the end of the line to tell you whether it was actually used. And then the option CMDS echoes the GLOBK command file, the outputs, and the glog command files as you go across. So program flow, we read all those headers, we apply all those renames, etc. that we have in the EQ file, sort it as a function of time, initialize the Kalman filter with all the a priori constraints that we've done, read the H files one at a time, run a sequential Kalman filter, we compute the chi-squared increments between each, the coordinate adjustments and rotations implied by the new data, And if they're all within tolerance, we update the solution and write the chi-squared into the log file. And then we iterate that for every one that we come through. When it's finished, you write out the sol file and the print file, again, if you've told it to do that. And then we optionally invoke glog to apply the constraints with the stabilization, apply any linkages between parameters, there's equates, force, and constraint options, compute the chi-squared increments of doing each of those. We can estimate plates using the plate command, and then we can write out the solution in the glog output file and potentially save the solution both at this point before glog runs and also a save after glog has run. So the things GLOBK cannot do. It can't repair problems in the original analysis. So if you had cycle slips in the GAMIT solution, which you did not know about, did not get corrected, and it's caused a problem, we can't fix that. If you use the wrong antenna phase center model, which I've been stressing a lot, we cannot fix that. If you use the wrong antenna height, we can fix that because that's just a geometric change. And there's a program called HF Update that allows us to do that. We recommend you don't try to do that. We recommend that you get the antenna information correct. That's one of those critical pieces of information. But if you did make a mistake or somebody else, always blame somebody else who made the mistake, then HF Update could be used to fix that. We don't resolve ambiguities in GLOBK, mainly, again, because the file would be massive if we tried to do that. One of the reasons GAMIT takes so long to run is because it's carrying all those ambiguity parameters in the estimation of that. We cannot overcome nonlinear effects. You saw those partial derivatives of the Taylor series expansion this morning, and then the plus ... the second order terms. You want those second order terms to be small and negligible. And if they are not, we can't fix that in GLOBK. You have to go back to the phase processing in GAMIT to fix that. We can delete stations to stop them contaminating the solution. And I must admit, with most modern GPS data collections these days, it does seem you can have a very corrupt station in the solution, something with very large variance, for example, and it does not actually seem to influence things around it too much. If you had a really close by station, it probably would. But in general, we find that if you have a bad station, and then you go back to GAMIT and rerun it without that station in there, the answer you get is not that different from what you get in GLOBK just by eliminating that station out. That's probably not a universal rule, but that's what we seem to be seeing. So the a priori files in GLOBK processing, in GAMIT, you need them to be better than 10 meters for all the sites and cycle slip repair. Final adjustment is less than 30 centimeters. The accuracy of the constraint sites typically is around about 5 centimeters or so is fine for that. So for GLOBK, when you're invoking glog for the reference frame, the glog file is normally usually optional how good it is. If you're not invoking glog, then you need an accurate a priori file for sites that are constrained as you go across. For complicated renames and equates, the APR file should be made consistent with that. And we'll see that when we look at some of the utility programs like TSFit, again for large data sets, we now have a much cleaner way of creating these APR files. glog, the API file, needs to have for the reference frame sites. Those are the ones that have to be accurate. And for anything where you're doing equates on parameters as you go across. So what can go wrong in GLOBK? H-file is not used. You'll see that as it gets deleted, that would get deleted because of a high chi-squared increment when it comes through. And that sometimes can be due to a bad station. This often happens with survey mode data where often there is a main mark and a recovery mark. Or it would happen with your station where it had moved 10 meters. If we didn't acknowledge that that had happened, anything that that station was involved in would generate a high squared and would get thrown out. Since we run in time, that would throw out all your Leica data because the solution would have been established already for the Trimble site. So the high chi-squared increment, inconsistent data. If you are using relaxed mode and merging with, say, the orbit files from MIT, the GLX files that we supply, that can have real issues if the modeling of things like the albedo and the gravity field are different. That's one of the reasons that we recommend baseline mode, because if you're going to do orbit estimation, you really do need to understand a lot about what you're doing in terms of orbital dynamics and what are the models that are actually being used that. The station is sort of completely missing. You think it should be there and you don't see it. Well, one thing it could it might have not been present in the H file originally, you just didn't realize that. or you may have renamed it out of existence accidentally. And there's a program called GLList, where you can give it the GDL file and then an output list file, and you can actually give it all of this command files, not the command files, but you can give it the earthquake files that you're using in GLOBK, and it will do all the renaming and tell you what you should expect in your final run as you go across. In GLOG, the stabilization fails. That's often because you have too few sites in it. Again, we have enough IGS stations that with 10 of them at any one day, we should have most of them around. Large uncertainties, that can be, again, due to a poor stabilization. That may be due to poor geometry of the reference frame stations you're using. In some cases, you have uncertainties that are too small for some of the stabilization sites. And again, that's basically bad coordinate geometry, and where something like the rotation parameter, if it's a station well away from everybody else, the rotation will be absorbed and it will get a very small uncertainty in there. High chi-squared, when you're doing increments, can be due to just inconsistent data again. If it's a post-seismic after an earthquake, for example, it may well be that there is a systematic change in the velocity after the earthquake. We're still debating how much of that actually happens, but that can cause a high chi-squared. And sometimes it can be because you have a different velocity estimate in the equated sites, and that's unmatched in the a priori coordinates. So the associated programs with GLOBK. H2Global we've already talked about. It does the conversion. Global to SINX is the inverse. It generates SINX files from binary H files. So if you want to share your results with someone who maybe used Bernese, you can send them a SINX file out of GAMIT, and they should be able to use it, hopefully. GLList lists the contents of a series of H files. HF update updates binary H files for changes in station.info or the SINX header information distributed by that. But again, it's really for antenna height changes, not antenna type changes. TSSum, TSFit, and TSCon are time series analysis programs that are written in batch. TSSum is the program that actually extracts the time series out of an org file and puts them into site-dependent files. It appends to the existing values that are there typically. TSFit is a fitting program that allows you to estimate positions, velocities, annual sines, cosines, post-seismic earthquakes, etc. It will read earthquake files from GLOBK. We often call this a prototyping tool because it allows you to essentially take all the inputs you're going to use for GLOBK. If you've generated the time series reasonably well beforehand, you can use all of those earthquake files, run it through TSFit, and make sure all the stations fit well, that you haven't missed a big offset somewhere, or there's an earthquake you missed or something else. And so once it gets through TSFit that way, you're fairly sure that when you run GLOBK, which is going to be a much longer process, it will fit okay. TSCon is actually a conversion program. It is useful. You can actually read time series from a number of different groups around the world, JPL, University of Nevada, and various other things. And not only does it convert them into the GLOBK time series format called .pos files, it will also do the reference frame realization the same way essentially as it's done in GLORG. So you can actually re-rotate other, so if someone sends you time series in ITRF 2008 and you want to rotate those time series into the Indian reference frame, you can use TSCon to rotate the time series and generate time series in a new reference frame. Again, using a set of stabilization sites and a set of a priori coordinates, exactly the same commands and formats that you'd use in GLOBK work in TSCon. Then there's the MATLAB-derived programs, VLView and TSView, which we're still having issues with. MATLAB, unfortunately, you have to pay for as a program. There's an executable version, but right now, that executable works fine on our Ubuntu systems, but seems to have a library issue on your system, which we hope your computer science guy will work out how to solve. Okay, so the summary. GLOBK has many features, and actually, due to its evolution, there tends to be multiple ways of doing some things. As we've actually changed our mind, or it's sort of evolved ways to do things. There's extensive help in the GG help directory and discussion and documentation. So the GLOBK help file is very, very long. The GLORG help file is very, very long. It gives you lots of information about how to do these things. And GLOBK, as I said, that's where all your major analysis decisions actually get made, and then it's quite complex and large. And experiment in testing your ideas on how to use different options is one of the best ways to learn the software. So some of the questions you could ask yourself is, I'm estimating positions and velocities, and we can actually do this with our data set. What if I turn the APR tran command on and off in the GLOBK command file? What's that actually do to my result? How much impact does it have? How do my uncertainties change if I change the APR northeast up and the APR MAR commands? What's the impact of changing those things? And so there's lots of things like that that you can experiment with as you go through. And I think, yep, that's the end of it. Okay, questions? It's lunchtime. Yeah. No, there's two types of command files, GLOBK and GLORG. GLRED,
It's almost similar.
GLRED is the same. It is the GLOBK command file.
Okay, if we are running GLOBK and GLRED, it will create the same .gl.
Yeah, the only difference is GLRED. So you have a list. The simple case is you have a list of, we'll have a list of 30 H files on our solution. When we run GLRED, it will take each of those H files and do to it what the GLOBK command file says to do. If we run GLOBK, it'll take the 30 H files all together, run the sequential Kalman filter, doing what GLOBK said to do. So they're both doing it, they're both running GLOBK. It's just that in GLOBK, all of the files are combined together as a sequential Kalman filter. In GLRED, each one is done separately as you go through. And that's the distinction between.
Which one do you have to use for time series estimation?
Normally you'd use GLRED for time series estimation.
For the rest we use not.
Yeah, and again, you are using, so if you want to do time series, you can set up 30 individual GLOBK runs for each day and generate the time series. Or, and you want to do the velocity solution, you would have just the one GLOBK run with it all done. Or you can have just one GLRED run that it will generate the 30 commands to run GLOBK. So that's all GLRED is doing, is it's just an interface that sequentially runs GLOBK on multiple things. But you can do it by hand if you wish to. You don't have to use GLRED.
Okay, one more thing. This code will convert time series from one program frame to another program.
Yes.
Similarly, what program we can use to estimate the velocity and the
TS-FIT. So there's a couple of ways you can do different reference frames. You could use TS-CON to rotate the time series into the new reference frame, and then use those new time series in TS-FIT to get the velocities. Or you could fit the velocities in the original reference frame, and then use a program called VELROT, which will rotate them into a different. Now the trick with VELROT is you have to in VELROT you give it the Euler pole to rotate it about. So if you were going from the ITRF no net rotation frame, say to the Indian plate, using the standard Euler poles to do that, both of those approaches would give you the same answer. But in general, when you so in general, VELROT, you have to give it the Euler pole implicit in the names of the plates you give it. Whereas in TS-FIT or in TS-CON, you'd be giving it a set of stations to use to rotate onto a set of coordinates. And that set of coordinates you probably would have generated with CORCOM, which allows you to rotate into different reference frames, an APR file. Okay.
Yeah. Example, you showed that there is a
prior noise and there is a mark.xxx, that
Right.
Process noise. The process noise means the computational process noise introduced by a computational process of Kalman filter,
Yes, it's
because of the numerical errors like that.
yeah. So in a Kalman filter, the evolution of the model is that you have a certain uncertainty now. The process noise, that position will change randomly.
Right.
And the process noise is the variance of that change.
Right.
And so that just gets incremented forward. You hope your next block of data
Okay.
has enough uncertainty that it undoes that change. And so typically you will reach sort of steady state.
Okay. So actually it's a prior noise. It is reducing, and then you reach to steady state after few iterations?
No, actually, it doesn't have to reduce. It can grow.
Grow also.
Well, the process noise grows always,
Okay.
but the data that you're bringing in
That is-
causes it to come down, and then it's the balance between those two.
Okay.
So if your data is really precise,
Right. Then it will happen that
it'll go down.
Other it will grow
If the data is not very good, it'll go up.
because process noise will add it to.
Yeah, the process noise adds noise, the data takes it back out again.
Oh. And what do you mean by quasi mode? You were to what?
Oh, it's because there's not really observations. It's derived parameters.
Okay.
That's why it's
Not
quasi.
direct observation.
Yeah. So a standard Kalman filter, you would think about having data. Well, it's an interesting issue that in most estimation now, people don't think there's a distinction between data and parameters
Okay.
because all the data we use is in fact parameters from some other filter. So the phase measurement we get from a GPS receiver is not a measurement of phase. It's the output of a state vector from a Kalman filter running inside of that receiver.
Okay.
So it's not really, but at the time, back in 1990 when we did that, we'd try and just differentiate between the notional observations and parameters, which we call quasi.
Okay.
But that's the reason for the quasi.
Kind of quasi observations and original observations.
Yeah, it's sort of, you would,
Derived observations and the original observations.
The-
The moment you use derived observations.
yeah, it's a derived, it's a derived observation.
Generally, we use for inertial frame, we call it quasi-inertial.
Oh, quasi, yeah, but quasi just simply means sort of, right?
Okay, sort of. Not
Yeah.
exact.
Not exact. So, yeah, that's why they're quasars. They're sort of stars, quasi-stellar objects, QSOs.
Okay.
It's that.
They are not exactly stellar objects, but they are like stellar.
That's right, and that's the same thing. They're like opposite. And if, as I said, in hindsight now, I don't think there's a distinction between. There is true observation, right? There was the old telescopes where someone would look at a circle and write the number down.
Okay.
That's a pretty pure observation. But you don't do that anymore, right? You press a button on the total station and the number comes out. And that number is coming out from some computer algorithm in there, deriving it by doing an interpolation across some optical surfaces. So it's not, even that is not really an observation anymore. That is coming from some estimation system itself inside that receiver. So, okay.
The constraint is the moment I provide a low value of variance to a variable, I'm trying to constraining it.
Right.
Right? That's the meaning I come.
Yep, that's right. Low, yeah,
And
small
the moment
variances.
you get a large constraint, it's loose solution.
That's right.
Okay.
Yeah, if you do, yeah, but large variance is a loose solution.
Anyone else?
Sir, when we call for any GLOBK operation by typing APR underscore XXX,
Yep.
if you are giving any U, then it will take parameters in state vector according to that, or every parameter is taken.
So when you say APR northeast up, the next thing you give it is either the name of a station or all. And if you say all, then the next set of values you give it will be applied to all stations. And then, so we generally, if we were to be constraining stations, we normally would have then a line which would be APR northeast up, HYPD, whatever hyperdad is, and we might give it a centimeter constraint or something like that. But generally, when you invoke it, it's applied, and then subsequent applications replace whatever is appropriate from what you originally had.
Means size of state vector will vary according to this.
The size of the state vector in the Kalman filter is going to depend on which things you are actually estimating. So it would depend on the number of stations. In principle, I suppose, that's an interesting test. We've never done that, but you can actually say APR northeast up for a given station, and if you say 0, 0, 0, 0, 0, 0, it'll actually take that station out of the state vector, and or reduce the size of the state vector. I've never actually done that, but that work.
That's one thing more. Generally, we study about Kalman filter taking white noise,
Yes.
and here you are taking colored noise.
The process, the random walk process noise is actually a colored noise. So, but that random walk is driven by a white noise process. And so the nice thing about a random walk process, which means that if you know the state vector now, the state vector at some future time only depends on the current state vector and what happens in that time in between. So that's a Markov process. But other processes you might have heard of are called flicker noise. Has anyone heard of flicker noise? The problem with flicker noise is that evolving from this state to the next state only depends on what happens in this interval. It also depends on all previous history. Flicker noise is horrid that way. That's why you cannot write a Kalman filter with flicker noise. If you, the state vector would actually literally be the full length of all of the data you have, because a flicker noise process, what evolves next depends not just on what happens now, it depends on what happened 20 years ago.
Means we will not go sequential.
Sorry?
Means we will not going sequential with flicker noise.
We're not going to consider flicker noise. So if you want to do flicker noise in a Kalman filter, the most common way people do it is by stacking together multiple first Gauss-Markov processes with different correlation times. And you can build up a synthetic version. So what happens is, over a certain frequency range, it can look like flicker noise, and then at low frequencies, it ultimately becomes white noise, and at very high frequencies, it becomes a random walk. But that's an approximation you can do. That's an awful lot of stuff you have to add in the state vector to do that well. And so again, flicker noise in Kalman filters just do not. Flicker noise, if you're going to process it, you may as well do it with the least squares. And build, so in least squares, you can do Kalman filtering in least squares as well. It's just that you have your parameter estimates then in your least squares problem would, instead of be estimating one station coordinate, it would be the beginning station coordinate, and then normally say increments of the station coordinate for every time you had measurements. And so you would have actually many more parameters than data, but you have a priori constraint matrix that you put a priori on the process noise model. And it's that a priori constraint matrix on those parameters that will allow you to actually get that solution. So you can formulate a least squares problem. You can formulate a Kalman filter in least squares. It's just that the solution becomes massive, and you have every single epoch becomes part of the parameter estimate that you're making. And but again, it's and you can play some games to speed it up. But yeah, there's nothing magical about least squares. Kalman filters are a least squares estimator. Yeah, and except that it's balancing not just fitting to your data, it's also balancing fitting to the process noise model as well. In the same way as when you do a constrained least squares solution, you're balancing fitting to the data and balancing to those a priori constraints. And it's just really, in a sense, the nature of the a priori constraints that you would put into a least squares solution which has a priori constraints. But as I said, the parameter list would be massive if you were to. But we actually, I must admit, when we're in Kalman filters, we do that. If you're doing simple problems with just a few hundred parameters, say if you're doing a few hundred time steps for the station coordinates and 3 coordinates. So in a least squares approach, that would be a 900 parameter solution. The Kalman filter would be a 3 parameter solution done sequentially. And if you want to compare them, you can actually run those two. And when you do it with least squares, your solution gives you the full back solution at the same time. And it gives you all the correlation. That's why it takes so much longer, because it actually is telling you all the correlation between every different time. That's what's coming out of that big covariance matrix. When you run a back filter with a Kalman filter, it gives you essentially the variance as you go back, but it does not allow you to calculate easily the off-diagonal terms. The correlation between the value at time t10 and time t20, you never get that piece of information. And that's why it's faster. And literally, you are not computing most of what would actually get computed in the least squares solution.
Instead of processing diagonal values.
The random, most of them, actually, it runs, GLOBK actually runs in Cartesian XYZ coordinates. And so when you give it certainties, that into E, if you give it if you give it the same values for northeast and up, then in rotated at XYZ, that is just that same number. But if you were to give it 1 meter for the horizontals and 10 meters for the vertical, it would actually have a full variance covariance matrix, a little, 3 by 3 covariance matrix in XYZ space. But in it's basically the process noise is diagonal across it, yeah. And of course, the input data covariance matrices are full matrices. The things coming out of GAMIT, when you look at that H file, it is literally a, well, for our solution, we're doing 10 stations, so it's 30. It's small. It's a 30 by 30. Yeah, 30 by 30 matrix that gets written out, but it's a full matrix. And if you're doing 50 stations, it's a matrix. That full matrix is used. That's again what takes time. That's why the time series analysis programs like TSFit, which operate on one station at a time, the reason they are so much faster is because they're not carrying all the covariances between all the individual stations. Those are just treating each station by itself. And so GLOBK is carrying all that covariance information, and that's what makes it slower, because it has to do all that calculation on that.
I have a small question. That when you said we cannot process 50 to 60 stations all together.
Oh, you can do 50 to 60 together.
Oh,
You can't do 500 together.
Okay. So when we are putting the two different processing, so let's say 15 station in one processing and 15 station in two. Second, they could have been processed together.
Right.
Matrix, variance stress matrix from the GAMIT processing has been 90 cross 90.
Yeah.
Full variance matrix. But when we are combining 15 and 15,
Yeah.
GLOBK.
Yeah, you do. Yeah, that's what I was saying about modern GPS, is that when you actually look at what those elements are, they're actually quite small. And it's an interesting, we've debated this, but when we formed that double differenced operator, and I'll just look at this. So I have a network here. So say that's what my network looks like. Now, and just for the simple case, I'll say, okay, I'm going to form double differences between these stations, like that, and I'm going to form double differences between these stations like that. That's perfectly legitimate. And now, to link the two networks, I'm just going to form the double difference across between this pair of stations. So when you look at the way that forms, that actual normal equations you form is not different to including this station in this network and including that station in this network. And so, so you end up essentially using this data twice. But it's a very small contribution when you do that. And so it's that, that notion that you can form all the double differences over here and all of that. And this sort of, ultimately this breaks down in large networks because we have so many, we do have crosstalk that go across. But again, the tests we've done of actually doing exactly what you said, two 15-station networks, overlap them with, theoretically, one station is the only thing you have to overlap between them, and then comparing them to the 30-station network. That's a really close comparison in general. Now, in general, when we do the overlap, we actually overlap a couple of stations for redundancy. And in theory, okay, when we can combine, we can break that overlap by renaming one of those overlap stations in one of the networks to a different name. And then it's like a different station. So you can play around with this if you want to. And again, that's the sort of thing we recommend that people do. Is a lot of this is you gain experience by thinking about, exactly as you had said, you think about different experiments that I might do. And if you keep them small, you can do them fast. A 15-station network, we know is going to not take very long. And a 30-station network is going to take maybe 8 times longer. It'll take about 8 times longer. But it's still a short amount of time. And so you can play around and make sure your intuition about what you think should happen is going to happen. And you can also then play these games of, overlapping more stations and see what the impact is. And then the impact of sort of forcing them apart when you run GLOBK. So yeah, it's a lot of this is intuition gained by experimenting and having thought experiments in your mind of what do I want to do and what do I think is going to happen when I do that. And then if it doesn't, rethink about, well, what did I not get correct? Or what was my conceptual model not right about that? So that's what we highly recommend, particularly in programs like GLOBK, as I said, this last thing here. Play around and see what the impact is. A lot of stuff, I must admit, a rule of thumb we have when you're doing this type of comparison is that when you're comparing things, if the differences are small compared to the standard deviations, and by small, I generally mean something like less than half a standard deviation different, then generally you consider that to be, that's the same answer. So there are certain things you do where you expect the answer to be exact to 10 significant digits. But much of this, when you're doing data analysis of this type, agreement really is relative to how small the uncertainty is. So if you only can determine something for a meter, and you see a 10 centimeter difference when you do it different ways, that to me that's in the noise of the estimate itself. If it's good to a millimeter, you expect to see less than a millimeter differences when you do things. And I think actually later on next lecture, at the very end of it, I'll show you some examples of comparison. The question you basically asked in some sense is, well, what if I do the solution in GLOBK versus I do it from time series and TS-FIT? How much difference does that make? And I must admit, these days, if you have a well-defined reference frame, it actually makes very little difference at all. But to generate the time series, you need that well-defined reference frame first. And so to get that reference frame, that's what GLOBK is designed to do. And once you've got it, you generate time series in that reference frame, then everything seems to match. And that can actually make your solutions much smaller, because you may want to have only 50 sites, depending on how big your thing is. But you can have a small number of sites in the reference frame, so you'd run GLOBK with that small numbers of sites, but then generate the time series for many, many more sites. And then as I said, the answers you get tend to be very, very close. And again, on that criterion, do they differ relative to their standard deviations? In other words, what's the chi-squared of the difference, in a sense? Okay.
Okay, so